Every minute, 2,000 glass bottles get tossed. Most people think that's the end, but those bottles are about to be fed into a furnace hotter than a volcano. 2,700 degrees, and spun into a fiber that stops fire cold. That pink insulation in your attic? It's made from old glass, the same glass that could save your home from burning. It's the most overlooked transformation in construction, and it's absolutely brilliant. Here is how it works. This is fiberglass insulation. It lines 90% of American homes, yet almost nobody knows it starts as beer bottles, pickle jars, and shattered car windows. The real question isn't just how that transformation happens. It's why a material designed to stop a house fire is made from something so fragile in the first place. The answer begins in the furnace. The furnace doesn't just melt glass, it erases identity. A beer bottle from last weekend, a pickle jar from a deli in Chicago, the windshield from a wrecked sedan, they all enter the same inferno. And inside, the glass forgets everything it used to be. The scale of this forgetting is staggering. Every year, the United States throws away over 7 million tons of glass. Only a third gets recycled. The rest sits in landfills, where a single bottle can take 1,000,000 years to break down. But the glass that does get collected ends up here. Massive sites where trucks dump mountains of shards onto conveyor belts. Magnets pull out metal. Screens shake off labels. The shards get crushed into a fine grit called cullet, a substance that looks like dirty beach sand but holds a secret. It melts at 2,600 degrees Fahrenheit. At that temperature, something strange happens. Silica, the core of glass, becomes a liquid so obedient it can be spun into threads thinner than human hair. The process was discovered by accident in the early 1930s. An engineer at Owens, Illinois, was trying to weld glass blocks with a jet of compressed air. Instead of sealing the glass, the air blasted it into a cloud of fibers. He had stumbled onto fiberglass. Patented in 1936, the material was originally a curiosity. Then builders realized those glass threads had a trait no one expected. Fire couldn't touch them. Glass fibers are non-combustible by nature. They come from sand and limestone materials that don't burn. When woven into bats and blankets, they create a barrier that can hold back flames at over 1,000 degrees Fahrenheit. That's why building codes now demand insulation like this. Not just to keep heat in, but to keep fire out. Today, companies like Knauf and Owens Corning consume staggering amounts of cullet. In a single year, Knauf alone recycled more than 800 million pounds of glass. The economics are brutal. The machinery is unforgiving. And the furnace at the center of it all runs 24 hours a day, 7 days a week, because shutting it down would turn the molten river inside into a solid tomb. But the thing that surprises even the engineers who run these plants is not the heat. It's what happens to the glass right after it leaves the furnace. Because the moment those molten threads hit open air, they face a problem that could ruin everything. And how the industry solved it is the most ingenious part of the entire process. The problem is physics. Molten glass threads, pulled thinner than spider silk at 2,000 degrees, cool almost instantly in the open air. They become brittle. Untreated, they would shatter into dust the moment a worker touched them. And dust is useless as insulation. So before those fibers travel even a few feet from the furnace, they pass through a curtain of mist. That mist is a binder, a chemical cocktail that coats every strand. This is the moment that transforms a fragile cloud into a resilient blanket. That binder is typically a phenol formaldehyde resin, the same family of chemicals used in plywood glue and brake pads. When it cures, it locks the fibers into a springy, three-dimensional web. The web traps still air, and still air is what stops heat. The glass itself isn't the insulator. The dead air pockets between the fibers are. The glass just provides the scaffold. But here is the twist. That binder has a dark side. Phenol formaldehyde releases volatile organic compounds, or VOCs, as it cures. The same material that makes fiberglass fireproof also produces fumes that regulators have been tightening for decades. In the 1990s, the industry faced a reckoning. environmental agencies began classifying formaldehyde as a probable human carcinogen. Suddenly, the insulation that protected houses was itself under scrutiny. The manufacturers fought back with chemistry. They developed bio-based binders that used plant sugars and starches instead of formaldehyde. Today, many brands proudly label their products "no added formaldehyde." But the shift wasn't easy. The new binders had to withstand the same furnace-level heat, the same installation abuse, and provide the same fire resistance. A binder that breaks down at 500 degrees defeats the entire purpose. The engineering of this transformation is invisible to the public. Walk into any home improvement store, and you'll see rolls of pink, yellow, or white insulation. What you won't see is the 24 hours that roll spent inside a curing oven, where the temperature is held at over 400 degrees Fahrenheit to set the binder without igniting it. Or the fact that the glass used in that roll came from a cullet pile that contained everything from wine bottles to laboratory glassware, all ground to sand and then reborn. The scale is vertigo-inducing. A six-pack of recycled beer bottles yields enough fiberglass to insulate an entire wall cavity. 714 bottles can do a whole attic. In California alone, fiberglass manufacturers consume over 180,000 tons of cullet annually, with an average recycled content exceeding 50%. Every ton of recycled glass saves over 1 ton of raw materials and cuts air pollution by 20%. This isn't just construction. It's a slow-motion environmental loop. But the process hinges on one terrifying bottleneck: the furnace itself. It gulps natural gas constantly, sustaining a heat that can liquefy solid rock. Inside, the molten glass churns at 2,700 degrees Fahrenheit, glowing a fierce, blind white. If the gas supply falters, if the refractory bricks crack, if a power surge hits the control system, the entire river of glass can freeze solid in minutes. Removing a frozen furnace is a demolition job that costs millions and can kill, which is why the plants never stop. At Knauf's largest facility, the furnace has been burning without pause for over 15 years. And yet, the most dangerous moment is not inside the furnace. It's a few seconds before the fibers are born, because the molten glass must travel from the furnace to a spinning machine called a centrifuge. The centrifuge spins at over 3,000 revolutions per minute, flinging glass outward through microscopic holes. If the temperature drops even a few degrees during that journey, the glass clogs the holes. If it rises too high, the fibers don't form at all. That narrow window, barely 100 degrees wide, is where the job is won or lost every second of every day. And there's one more variable that nobody outside the plant has ever seen. It's what the workers call the birthmark, a visual flaw that appears when the recipe is wrong. And when it shows up, the entire product line, worth $250,000, can be condemned as scrap. The birthmark is a color aberration, a purplish streak that appears in the bats when the glass recipe drifts. It signals a chemical imbalance, too much boron, a spike in iron from a stray bottle cap that made it through the magnets. The insulation still looks pink. It still feels fluffy, but that birthmark means the fiber chemistry is off, and that means the fire rating is compromised. And that's the nightmare that keeps plant managers awake. Because you can't test every square foot. Quality control relies on sampling, pulling a few bats from each shift and torching them in a lab. But the batch that leaves the factory with an invisible defect could end up lining the attic of a school, a hospital, a home where someone forgets a candle. And in that moment, the material that was supposed to hold back the flames could do the unthinkable. But the industry's challenge goes deeper than the birthmark. The push towards sustainability has created a paradox. Recycled glass is environmentally essential. It cuts energy use by up to 20%. It saves 0.7 of a pound of carbon dioxide for every pound of glass reused. But recycled glass is chemically promiscuous. A cullet pile contains soda-lime bottles, borosilicate lab glass, lid crystal from old decanters, ceramic contaminated curbside pickups. Each shard melts at a slightly different temperature. Each contaminant shifts the viscosity of the molten river. The furnace operators become alchemists. They sample the glass constantly, adjusting the mix of silica sand, limestone, and boron to compensate for whatever chaos the cullet brings. An operator at a Knopf plant once described it as cooking a gourmet meal with dumpster ingredients. If they get the recipe wrong, the product fails. If the product fails, they lose hours of production. If they lose production, the furnace starts to cool, and the frozen glass scenario inches closer. The entire operation is one bad batch away from a multi-million-dollar catastrophe. And yet, there's another transformation happening with the same raw material. It's called foam glass. While fiberglass spins glass into threads, foam glass bakes it into a rigid block filled with millions of sealed bubbles. Crushed glass is mixed with a blowing agent like limestone, heated until the glass softens, and then the agent releases gas, puffing the glass like bread dough. The result is a fireproof, waterproof, rodent-proof insulation board that can bear enormous weight. It's what lines the tunnels beneath cities and the industrial pipes that carry superheated steam. Foam glass was invented by accident, too. In the 1940s, a Pittsburgh Corning researcher was trying to make glass stronger. Instead, he made it expand. The substance is so inert it can sit in a chemical bath for decades without decaying. Its fire resistance is absolute. No binder to burn, no fibers to melt and collapse. The material itself is essentially lava rock, already frozen, able to withstand over 1,000 degrees Fahrenheit without flinching. But foam glass is expensive. It costs 3 to 5 times what fiberglass bats cost. So the world still relies overwhelmingly on the spun version, and that means the race to perfect fiberglass never stops. Engineers now embed infrared opacifiers into the fibers to trap more heat. They tweak the binder chemistry to withstand higher temperatures. They weave the bats denser, layer them, face them with fire-rated foil. The culmination of all this effort is a test. A full-scale furnace test where a wall assembly is blasted with flames at 2,000 degrees. On one side, the fire rages. On the other, a technician stands calmly, fingers against the wall. The insulation must hold back the inferno for an hour, sometimes 2. In that room, the stakes are not abstract. The difference between a good batch and a bad one is measured in human life. This is where the story of a beer bottle comes full circle. That bottle, tossed into a bin, crushed to powder, melted in a sun-hot furnace, spun into 1,000,000 glass threads, and coated in a chemical shield. That bottle becomes the quiet pink barrier that stands between a family and a fire. And what happens when the flames finally meet that barrier is the only test that really matters. Inside the test facility, they call it the burn wall. A room-sized assembly framed with steel studs, packed with insulation, and faced with drywall. On one side, 32 natural gas jets ignite simultaneously. In under 3 minutes, the temperature on the fire side hits 1,600 degrees Fahrenheit. The drywall crumbles. The studs begin to glow. And the only thing standing between the flames and the cold side is the insulation. For the first 20 minutes, nothing visible happens. The pink blanket darkens. The paper facing vaporizes. But behind the char, the glass fibers hold their shape. They don't burn because glass is already oxidized. There's nothing in it left to combust. The silica and soda lime that began as a bottle in a recycling bin are now an inert shield, and the 1,000-degree heat only makes them more stable. At 45 minutes, the steel studs on the fireside deform. The binder in the insulation has long since cooked away, its organic molecules stripped into carbon and water vapor. This is the moment engineers lose sleep over. Because if the binder was flawed, if the birthmark was present and missed, the bats collapse. Without the binder's residual structure, the glass threads sag, gaps open, and fire punches through. But if the chemistry was right, even after the binder dies, the fibers interlock enough to maintain a barrier. The dead air pockets persist, and dead air still cannot conduct heat. At 60 minutes, a thermocouple on the protected side reads just 220 degrees. Hot enough to feel through a wall, but not enough to ignite wood on the other side. The test passes. The insulation has bought an hour for sprinklers to engage, an hour for firefighters to arrive, an hour for a family to wake up and get out. That hour is the entire point. Fiberglass insulation is not a force field. It cannot stop fire forever. What it does is trade time, time that the material buys by sacrificing itself. The glass fibers eventually melt at over 1,000 degrees Fahrenheit. But in a house fire, that threshold is rarely reached before the structure itself is lost. And here is the final surprise. The bottles never really go away. The same glass that leaves the factory as insulation can be recycled again. At the end of a building's life, when the roof is torn off and the bats are pulled from the stud cavities, that fiberglass can be ground back into cullet, fed into a new furnace, and spun again into fresh insulation. The beer bottle you drank from in college could now be part of 3 different homes in 3 different decades. Glass has no memory, but it also has no end. It is an infinite loop. That loop is accelerating. New plants are coming online that use electric furnaces instead of gas, cutting the carbon footprint further. Scientists are experimenting with glass chemistries that melt at lower temperatures. And the cullet supply is growing. The more we recycle, the more raw material the industry has. Every bottle you drop in the bin today makes tomorrow's insulation cheaper, cleaner, and more fire-resistant. The pink stuff in the attic was never just fluff. It was a bottle that refused to be trash. It went through a 2,000-degree furnace, a spinning centrifuge, a chemical binder curtain, and a curing oven. And then it sat silently above your ceiling for 40 years, waiting for a fire that hopefully never comes. That's the deal it made. Every bottle you've ever touched still exists somewhere. Most don't make it back to a furnace. They sit buried, but the ones that do enter a loop that never closes, they become insulation that will outlive you, outlive the house, outlive the century. And someday, when that house is torn down, they'll be ground up again and fed back into the fire. The same silicon atoms spun into a new blanket, ready to hold back another flame. That's the quiet miracle happening behind the pink rolls stacked at the hardware store. If stories like this change how you see the ordinary, hit like and subscribe. We're documenting the invisible machines that build our world, and there is so much more to uncover. I'll see you in the next one.